Okay, welcome to day 2 of section 2.1. We're continuing our discussion on functions. Okay, so the first thing we need to talk about today is finding the domain. Of a given function. And the second one is finding information about a function from its graph. Okay, so these are sort of our two skills today. Let's go on to the first one. Okay, finding domain. Okay, so let's talk about graph first. Let's say you're given a graph that looks like this. Okay, so maybe it looks kind of like a semicircular region. Something like this. Okay, and it's very obvious, either from the instructions or from the graph, that this graph starts and stops within this given region. So this graph does not continue. These are not arrowheads. -2 is the first x for this graph, and 2 is the second x for this graph, so the last x. Okay, so you can tell from this graph that the domain is basically between -2 and +2. How can I tell? Well, look again at the picture. The entire graph is contained between these 2 points, right? The graph is perfectly continuous throughout that. You could trace your pen right over this graph and you never have to lift your pencil. You can go from -2 to +2 along this track, or whatever it is, and you find yourself not having to leave the graph at all. So basically the domain is between -2 and +2. In this textbook we will write that as -2, comma 2 with closed brackets. Okay, this is a chapter 1 notation that we actually skipped, but here it is. So also known as -2 to 2. Okay, the second thing we might want to do is a graph like this one. So it's the same basic graph, except it looks like this. Okay, so you have open endpoints. So what is the domain here? Well, again, the graph is contained between -2 and +2, right? But it is not including the endpoints. So you'd write -2 is less than x is less than 2. You would not include the equalities on those inequalities, right? This is also to be written in this class as -2, +2. Okay, so let me just say something about that. It looks a lot like I just wrote -2, comma 2, as if I wanted you to plot the point -2, comma 2, you know, left to up to. That's not what this means. This is what we call interval notation. Interval notation. And you did not use it in Algebra 2 at all. Okay? But it's called interval notation, and it is a way to write, to express the domain, or range actually, we'll get to later, where it's a little tidier. You don't have to write the less thans, you don't have to write the x. Okay, let's look at a third scenario. So in this scenario, we have the same graph. Okay, only this time the left endpoint is open and the right endpoint is closed. So this is open and this is closed. Okay, so when it comes time to write the domain, we would say that it is between -2 and +2, including +2, but notice I left -2 as an open endpoint, so I did not put the equality on the inequality. How do you write this in interval notation? Okay, so to write this in interval notation, what you do is you would write for the -2 a rounded parentheses, and for the +2 a squared off parentheses for a closed parentheses. Okay? You could also have this opposite situation where the left endpoint is the closed one and the right endpoint is the open one. I'll draw that real quick. But this is just notation, right? That means this is how we write these things. Okay, so what is the domain? Well, this time it's including -2 and not 2. Okay. Okay, so when you write your interval notation, you can write a -2 with an open bracket that is squared off and a closed bracket that is rounded. Okay, a couple little comments about this notation still. Suppose you have a graph that looks something like this. So I'm just doing some various cases. Alright, let's do a situation where you start with a closed endpoint here, and then it goes like this. But then there's like an asymptote here. And then on the right side, it comes down and goes off to the right forever. Okay, so how would you write the domain? Well, you can see that basically everything kind of starts at -2, right? So you would basically write that it is between -2 is less than x is less than 0. So notice that the vertical asymptote is at x equals 0. And the graph never actually contacts that line. That is a vertical asymptote. We don't allow a graph to actually touch that. Okay, so we would not include 0. But this isn't the whole domain. You can't just say it's -2 is less than x, less than or equal to x is less than 0. You have to also say that there's a right-hand portion to this graph as well. And that goes basically from x equals 0 all the way out to infinity. So basically it goes 0 is less than x is less than infinity. Infinity means all the way to the right forever and ever and ever and ever. Right? Okay, so now this expression means all x is greater than 0. So the way you've always written that in the past is just x is greater than 0. Right? So there's no reason to write less than infinity. Right? Everything's less than infinity. So you just write x is greater than 0. Okay, so the domain on this one is -2 is less than or equal to x is less than 0. X is greater than 0. Notice there's not really any way I can write this in one inequality. Okay? How would you write this in interval notation? By the way, you're not supposed to write AKA. I'm just doing that to show you that this is our new notation, that this is also known as. Okay, so you would write -2 and you put a closed bracket on it. That means we're including the point -2, right? And then you would do comma 0. The 0 is not included. And then you would go 0 to infinity. Okay, if you put an infinity in one of these brackets, you always use rounded parentheses when you're writing infinity. And the reason for that is you can't ever include it. You can never include infinity. So you would never put a square bracket on an infinity, either as a opening of a negative infinity or closing of an infinity. This is how you'd write it with rounded. Okay, here's our last one for that set. This graph looks like this. Something interesting just happened right there at x equals 4. Alright, so what is our domain? Well, our domain is basically all x is less than 4 and all x is greater than 4. So in other words, there is only one point here where x is not present, and that is this point right here. This is what we call a hole. It is a hole. The graph is basically existent everywhere except here. So it runs all the way from negative infinity to infinity. You can trace the whole graph without lifting your pencil, except right here we have this tiny little jump. It's not even a jump, it's just a slight break in the graph. You kind of have to lift your pen for just a split second, not even that, to get over that hole, and then you can put your pen back down and draw the rest of the graph. Okay, so to write this in interval notation, we would write negative infinity, So negative infinity all the way up to 4, and 4 to infinity. Okay, and then you would also be able to write this symbol here. This is the union symbol. So what I've done is I've taken I spelled symbol wrong. I've taken the left side and the right side of the graph and combined them into one single domain. But this is a reminder to skip over that point at 4. It's called a hole. It's not really a point. It's an absence of a point. Okay, so there's that symbol. Maybe you've also seen it, U that looks like this, upside down U, but we're not going to be using that one for this context here. Okay, so there's your answer to that one. All right. Next, let's go on and let's talk about determining information about a function from its graph. Okay, so determining information about a function from its graph. Okay, so I'm going to go ahead and sketch a graph here. It's going to look like this. Okay. Now, my graph is a little more complicated than maybe the graph in the book, okay? But if I figured if you could do a more complicated one, you can do the one in the book. All right. So this is at -3. This is -3. This is -2. So -1. And this is 0, of course. Okay. All right. And then this is at 1. And this is 2. And then the other part of the graph is over here. Passes through 4, and so on. Okay, so the first question I'd like to ask is to find the following. So let's find f of -2 and f of 4. Okay? Now let's go ahead and make our y-axis go 1, 2, 3, 4. Okay? All right, so what is the question asking for? Here's what they want. They want us to find what y is when x is -2. So this means what is y when x equals -2, and what is y when x equals 4. Okay, so do you understand the question? So this would be a matter of finding the point where -2 is on the x. So that would be this point if you're at -2, and this point if you're at 4. So you'll notice that both of them are on the x-axis. You could actually say that this point is -2, 0, and this point is 4, 0. Right? Okay, so I would say that f of -2 is 0, and f of 4 is 0. This is like saying y is 0 and y is 0 for these two x's. Okay, let's try another one. Okay, how about find f of 1? So what does that mean? Well, that would mean find the point where x is 1. So that would be like this point right here. This is the point 1, 2. So the answer would be f of 1 is 2. notice that f of 1 equals 2 means 1 comma 2 is on the graph. It means 1 comma 2 is on the graph. Maybe you never realized that, but that's really all it means when you see f of 1 equals 2. It means 1 comma 2 is on the graph. Very important concept. Okay, let's look at part C. Let's find an x such that f of x is less than 0. So what does this mean? This literally means y is negative. It means y is negative. You know, they didn't tell us where to look, so I'm going to look back at the graph and see if I can find a couple here. Well, I would say that anywhere over here to the right of 4, the graph is underneath the axis, right? Okay, so I'm just going to go with 5. Okay, so here's an example of a point right here. 5 comma negative 1 or whatever. 5 comma negative 1. So I'm just going to say x equals 5 is a sample answer. So sample answer means it's not the only answer. There's just one answer. What are some others? Can you think of some? How about x equals 6 or x equals 7 or so forth? It seems actually anytime you're on the right of x equals 4, it's going to be down below that graph. Okay, I also see some points over on the left. I'll highlight them in green. How about at negative 2.5? Right between negative 2 and 3, maybe at negative 2.5, we've got a point down there too, don't we? So at x equals negative 2.5. Okay, so you could actually do better than this. I mean, you could actually describe all the points. Okay. Okay, so that's what I'm going to do here. I'm going to actually copy and paste this graph over to the next page and keep working with it. You don't have to leave this page, I do. Okay, so this actually would be part D here. Keep looking at this picture. Okay, so how about this? Find all x's such that f of x is less than 0. Okay, so we already said that there were some points to the right of 4, right? So we already said that if x is greater than 4, we're dealing with points that are below the axis. I'll highlight that whole region in blue. See? So remember, this means y is negative. You already wrote that, okay? Y is negative. That's all it means, okay? That's true for any value greater than 4. Now let's look at other spots. The other spot we noticed was over here in the green section, anywhere between negative 3 and negative 2 on the x's, right? So anywhere in this region. Okay, so let's go and include that answer as well. How about between negative 3 and negative 2, or in our newest notation, we could write this answer as, let's not write and or here. We've got to be careful with the word and or in math. We'll just leave it as two separate answers here. So if we wanted to use our new notation, our interval notation, we could go with basically from 4 to infinity. That's actually the part on the right. And then between negative 3 and negative 2. And then we'll use the U symbol. Okay, so there's an example of how to extract information. Okay, all right. Okay, what else could we be asked about this graph? We could be asked the following. We could say, maybe it would ask us something like, how often does the line y equals negative 1 intersect the graph? Okay, so what you would do on that, what I would do on that, is I would actually draw the line y equals -1. Y equals -1 is this line here. Okay, and here's what the question is asking. It's saying, basically, how many times did that line, that purple line I just drew, impact my black graph? Well, it happened right here and right here. So I would say twice. If I had to estimate where they were, I would say x is approximately -2.5 and x is, I'm pretty sure, 5. So I used an inequality, I'm sorry, I used a squiggly equals sign when the value wasn't too sure, and I used an equal sign for the point I was definitely sure about. Okay, what's another question they could ask? Okay, here's a more advanced question. Give a value of A, let's put it this way, give values of A and B such that A is less than B and f of A is greater than f of B. Okay, so what does this mean? So let's go back and look at the graph. First of all, we need to pick two x numbers, right? Because they're asking for an A and a B. How do I know those are x's? Well, they are inputs, see? So we're looking for two inputs. A and B are two x values. Okay, that's our first clue. I know that because they're in the parentheses here. I just underlined them. Okay, and we know that A has to be less than B. So A could be like 1, B could be 2. But you can't have it where B is greater than, B is the lesser number. So you couldn't do like A is 1 and B is -1. So A has to be the smaller number. So just write a little note to yourself, A is bigger. Okay, and then what we have to make sure of is, here's the other clue, is that the y value when you plug in A is greater than the y value when you plug in B. So the y value at x equals A is larger than the y value when x is B. Okay, so let's see if we could find a spot on the graph like that. Okay, so here's what I'm really looking for. Watch. I'm looking for a point at A and a point at B. B being the bigger number. So A comes first, then B. A is on the left, B is on the right, just like I did here. And I want f of A to be greater than f of B. So in other words, I want it to be above B. Okay, so this is first and above. Okay, first and above. All right, let's see if we can find 2 points that look kind of like that somewhere on our graph. So going back, you can pick from many, many choices, but I was thinking we could pick 3 and maybe 4 for the B, so 4. 3 and 4. Those aren't the only choices. You could also pick A equals -1, B equals 0. You could pick that, see? All right, let's go down and answer that. So let's let A equal 3, B equal 4. This is one sample answer. Sample. Answer. Or you could do, like I said, A equals -1, B equals 0. And there are many others. You don't even have to pick whole numbers. Okay, you just have to make sure that what you're saying is true. Okay, so this brings up the concept of decreasing and increasing. What we have here is a portion of the graph where it must be going down, because we just went from A to B and it went from a high y value to a low y value. See the green I just drew there? Okay, so let's go and answer the last question for this. Name all values of x where f of x is decreasing. Decreasing. Okay. Alright, so this is our graph, remember? I just copied it into here. Okay, so where is it decreasing? So decreasing is easy to find. You're just looking for parts of the graph that are going down. So that'd be like this part, and really all of this. So I just scribbled it in green. But as you go from left to right, you find yourself falling. See that? You're falling. Decreasing, decreasing. So just this part's in green. But all of it. Okay, so what is the answer? Between -1 and 0, it seems like the graph is going down. And from 2 and onward, it's going down. So you could just put x is greater than 2. Or in our interval notation, we could write -1 to 0 in union with 2 to infinity. Okay, so it's a little bit of new notation there, a couple of new ideas. Okay, how do you find the domain given the function? Okay, if you're trying to find the domain, you're given a function. Let's say you're given f of x equals x squared plus 2x. This has basically the graph of a parabola. Okay, you probably remember that. So a couple observations. This is a parabola. Okay, and a parabola has domain all real numbers. Let me explain why. The domain is all real numbers. The reason I know that is because no matter what number I plug in for x, I always get one answer in the end. And there's no numbers for x that I can't plug in. So all x's can be plugged in. That's the first thing I noticed. And it's a function. Well, it's already given that it's a function. I was going to say it also only yields one output, but that's beside the point. I said in the instructions that it was a function, so all x's can be plugged in. Okay, graphically, a parabola looks like this. This one looks like this. And you can kind of draw a vertical line anywhere you want, and you'll contact the graph. There's not really any gaps in this graph. Okay. All right. How about this one? This one's not quite that way, is it? There's two numbers that you cannot plug in. You can easily find them by setting the denominator equal to 0. So if we set x squared minus 4 equal to 0, we get x squared equals 4, or x equals plus or minus the square root of 4. That is, x equals plus or minus 2. So x equals 2 and x equals -2 are excluded values, or you call them restricted values. So what is my domain? Basically, x is, let's write it two ways. In our old notation, we would say it can be basically anything it could be anything to the left of 2, anything to the left of negative 2. It can be anything between negative 2 and 2, or it can be anything greater than 2. These are the 3 answers. Okay, so what's going on is these are the only 2 places on the number line where you're not allowed to be, but it is everywhere else defined. So 2 numbers for x that cannot be plugged in. Okay, in our new notation, we would write that as negative infinity all the way up to negative 2, between negative 2 and 2, and from 2 to infinity. Okay, let's do another one. Let's do a function. How about h of t is equal to the square root of 4 minus 3t. Now, on this one, there's no denominator. On that last one, the reason we weren't allowing 2 and negative 2 is because you can't have 0 in the denominator, right? So this was not allowed to be 0. That's actually how we started our problem. In a square root, or any even root, we basically have to make sure that this is greater than or equal to 0. So a radicand, if you're dealing with an even index root, must be greater than or equal to 0. So we'll just write that and solve it. So you subtract the 4 over, divide by negative 3. Notice that I had to flip the inequality around. Okay, this is your domain. So your domain is basically t is less than or equal to 4/3, or you can write negative infinity 4/3 if you're using our new interval notation.